Hello, today we are going to talk about Catalan numbers. The Catalan numbers are a sequence of positive integers that appear in many counting problems in combinatorics. They count certain types of lattice paths, permutations, binaries, and many other combinatorial objects. They satisfy a fundamental recurrence relation and have a closed form formula in terms of binomial coefficients, which we'll talk about later in the video. Now, before we jump into the mechanics of Catalan numbers, let's talk about the origin of Catalan numbers and how they came into being. The oldest occurrence of the Catalan numbers were found in a book written in the 1730s by a Chinese mathematician and scientist Ming. The book included a number of trigonometric identities and power series, some of which included the Catalan numbers, just like this one. However, the integrality of Catalan numbers played no role in this work. The next person that we are going to talk about is Euler. In 1751, Euler introduced and found a closed formula for what we now call the Catalan numbers. He was assisted by Christian Goldbach and furthermore by Johann Sagner in the 1750s. The formula that he came up with was as follows. The problem with this formula was that he had only worked out the values for n equals to n less than 8. Now the real reason for why Catalan numbers are called Catalan numbers is because it was Eugene Charles Catalan, a French and Belgian mathematician, who was the first to describe these numbers as a sequence and give a well-defined formula for the nth Catalan number, which is shown right here. Now using this formula we can generate Catalan numbers. Here is the list of first few Catalan numbers. For n equals to 0 and n equals to 1, the corresponding Catalan number is 1. For n equals to 2, the corresponding Catalan number is 2, and so on.
Okay, so I'm going to be discussing a few applications for Catalan numbers. To name a few, there are a number of valid parenthesis expressions, a possible number of BSTs that can be constructed with n number of nodes, dig paths, and last, number of ways to tile a stair-step shape of height n with n number of rectangles. So I'm going to be discussing the very first one, then we'll move on. So the first one is the number of valid parentheses expressions, which the number of valid parentheses expressions consists of n number of right and n number of left parentheses, which altogether is equal to the nth Catalan number. Possible combinations of parentheses for n equals 3 can be this one, this, and this. Another application that I'm going to discuss is the binary search tree example. There can be several variations of binary search trees that can be constructed with n number of nodes of nth Catalan number. These are all the possibilities of BSTs that can be constructed. This is the first one. This is another. This is another one. This one. And this. So another example could be the dig paths. Few sequences also describe dig paths of length 2n. These are sequences of equally spaced northeast and southeast walks starting at the origin and ending on the x-axis. Also, the graph never goes below the x-axis. The bijection between acceptable sequences and dig paths assigns a plus 1 to a northeast walk A and a minus 1 to a southeast walk. The condition is acceptable when the path never drops below the starting and finishing line. These both paths should be equivalent. For n equals 3, the following paths are constructed as shown in this example. This is the first one, this is the second one, this is the third one, the fourth one, and the fifth path. The last example we are going to discuss is the number of ways that we can tile a stair-step shape like rectangles of height n with n number of rectangles. The following figure shows all the possible figures with case of n equals 4. So each figure shows there are a total of 4 rectangles because n is equals to 4.
Okay, so now let's build a function of Catalan numbers using one of the examples of the Catalan numbers, which is the triangulations of polygons. So what does it mean to triangulate a polygon? It means that that polygon is divided such that it can be seen as a group of triangles. These triangles must be non-intersecting, and each vertex of the triangle must also be a vertex of the polygon itself, right? So let's take a look at the triangulations of a foregon. In any diagram that has more than 3 vertices, you can actually use diagonals to make triangulations. So here are the only 2 triangulations of a square. Moving forward, these are the triangulations of a pentagon. These are 5 in number. So how does this relate to the Catalan numbers, right? So if we make a sequence of the number of ways to triangulate n plus 2 gons. So if we take n is equals to 1, we need to write the number of ways to triangulate a triangle, which is 1. And then if we take n is equals to 2, we must find the number of ways to triangulate a foregon, which is a square. And we already found that's 2. And then we did that for a pentagon, which is n is equals to 3, and that's 5. And you can really see that, it's really forming the Catalan number sequence 1, 2, 5. And then if you continue on, it makes 14 and then so on and so forth. So how does this help us in creating the generating function? So for this, we look at the octagon case. Now, what we do is that we number the sides of the octagon and we fix 2 sides, right? We fix 2 vertices. And the line, the base between the 2 vertices is fixed. And we know that if we that base must be part of at least one triangle in any triangulation. So using that, what we do is that we start building triangles, right? So over here, what we do is that, so the triangle that we will always consider will have 1 and 2 as 2 of its vertices. So now, first of all, we make 3 the third vertex, right? So we make a triangle looking like this. So now the number of triangulations with this triangle present is actually going to be 1 into the number of triangulations of this diagram. And since this is basically just a 1, 2, 3, 4, 5, 6, 7 gon. So 7 gon means n is equals to 5. So this is just the 5th Catalan number, C5. So moving forward, if we take the vertex to be 4, you can see that it's divided into the left and right. So over here, this is a 3 gon. So this is going to be the first Catalan number, and this is going to be the 1, 2, 3, 4, 5, 6. So this is going to be the 4th Catalan number. And since you can think of this as permutations, right? So we can put 1 in this place and we can put 4 in this place. So basically C4 in this place, and we can put C1 in this place. So we multiply them together to get the total number of ways in which a triangulation can take place with this triangle in the triangulation. So now let's move forward. Yeah. So if the third vertex is 5, the triangulations becomes C3 into C2. That's because this is 4. So this will be C2 and this will be C3, right? And then moving forward, if the vertex is 6, now you can see that when we had it with 5, there's just a left-right shift, right? So उसमें जो है वो ये वाला जो shape है वो इधर बन रहा था और ये वाला इधर बन रहा था, but now it's the opposite. So C2 into C3 this time, C3 into C2, same thing, but we're using this to actually make a sequence later on. So we did that for vertex 7 and vertex 8, and I would encourage you to do that individually. And we find out that the overall number for n is equals to 6 is the 5th Catalan number plus C1 into times C4 plus C2 times C3 plus C3 times C2. We've already done it till here, right? And then this part is the 7th and 8th vertex. So now, if we take a certain C0 is equals to 1, so if we assume that there is a 0th Catalan number which is equal to 1, we can write this as C6 is equals to C0 times C5 plus C1 times C4. So you can see that the sum of these, this index here and this index here is always equaling 5, which is n minus 1, or n if we take n plus 1 as the current Catalan number, and so on and so forth. So in general, we can write this as C n plus 1 summation n I from I is equals to 0 to n C I C n minus 1. So for the sixth, so for if we take n is equals to 5, that should give us the sixth Catalan number. And then you can see that this general form actually just traces back to this. So from here, Hamza Asad will take over.
Hello, Assalamu alaikum. I'm Hamza Asad, and I will be explaining how the generating functions for Catalan numbers work. So let's get started with defining what exactly are generating functions. So I want you to imagine like you have a sequence 1, 2, 3, 4 up till like n, or these are like basically the first n positive numbers. If I were to encode that in a function, if I were to encode that in a singular function, I probably would like try and to guess and check and see what mathematical formula corresponds to the sequence. And that is how you go about it. Like suppose if you want to like approximate sine x, you have Taylor polynomials for that. Similar concept here. So Taylor polynomials are basically a generating function for the trigonometric function, right? Similarly, if I were to generate a function for this, I would write it as 1 over 1 minus x to the power of 2, right? And how this would expand out, it will basically give us 1 to the power of x to 0, so that's basically 1, plus 2 to the power of x to the power of 1, so that's basically x, and then we have 3 x to the power of 2, and that's there, 4 to the power of x, that's 3, and up till like n to the power of x to the power of n minus 1, right? So that's like the basic function for generating the first n positive numbers, right? And notice here that the x variable has no real use or application in that. It's just a way of signifying, or you're sort of like giving an index to the term, right? It doesn't have any real use here, because we just want to like encode these sequences into one single mathematical expression. So this expression does it for this sequence, and that is called the generating function for the first n positive numbers, right? Similarly, if we have, for example, like if we have Catalan numbers, right? So Majid defined what Catalan numbers are, and if we were to write the first 4 terms of Catalan numbers, they would correspond to 1, 2, 5, and 14. So that's 1, 2, 5, and 14. And then if you remember, then there is a specific formula for it, which goes n e to the power of n summation of um sorry summation of I equals to 0, and then we have c of I, and then c of n minus I, right? So if I were to generate a function for this sequence, right, I would basically go about listing my Catalan numbers like this. So if I were to write the first function, number of Catalan number, I would write it as c0, and then we have c1, and we have c2, and then c3 up till c of n, right? And suppose that this is a sequence, right? We have encoded this into a sequence, then you'll remember that basically we'll add the x variable or any variable here, which denotes the index of the current iteration, right? So that's 1 x square, and then we have x cubed, and up till like c of n, and then that would be x of n, right? So these denote the index, and we need to find the nth Catalan number. We're not actually solving for the nth Catalan number, by the way. Here we are just basically trying to find out the generating function for this, right? So we'll basically call this sequence c of x, and we need to find out what c of x is here. So if I were to expand out these terms and replace the c's with the actual Catalan number, so we replace it with 1 here, right? That's 1, that's 2, 5, 14, and so on. Basically we would end up with this form of function, right? And these would basically correspond to like how they would expand. So if you want to expand 2 times x cube, you would basically have x cube plus x cube. And if you want to expand 5x to the power of 4, you would basically be adding x to the power of 4 5 times, right? And you'll notice here if we if we encode this into a bracket form, then we would end up with these weird looking things, and they have a special name for it, right? These are basically uh, formally called Dijk's language. There's a whole study on this, so I won't go into depth on this, but basically if you notice here, a pattern is forming that each term apart from the first two terms are basically a product of the two lesser terms, right? So you notice here, for example, take this term, for example. This corresponds to these functions, right? So these are basically, if you were to strip away the outer brackets also, then this is basically x times x multiplied by x and then multiplied by x. So if I were to break it down, I would end up with x dot x multiplied by x, right? So, and we have here that there exists x here, so that's the first term, and then we have x times x here, or we have x times x here. These can both correspond to this greater term, right? So this is basically a product of the two lesser terms. And if we were to like form a general equation out of this, we would notice here that all of these are basically squares. Apart from the first two terms, all of these are basically squares of the Catalan function, right? So we can write this as c of x whole square. And then obviously we would not be adding the first term here because we added this as like a part of the series. We would not be adding this into the actual function because this does not multiply with any other x here. So we'd simply be adding it as it is, and we can basically form an equation in this form, right? And you'll notice here that this forms like a quadratic equation, and we can solve for this actually, right? So you have the terms a, b, c here equals to 0, and applying the formula for this, applying the quadratic formula to this, it would yield the terms 1 plus minus um, and we're solving for c of x, by the way, not x. Notice, it's important to note here, we're solving for c of x, not x. So these are basically the roots of the c of x, not x. And this comes out as 1 minus 4 times of x over 2 of x. And you can solve it for yourself, you'll see that it's true. When we will expand this out, we'll notice here that we have plus and minus both, right? So how do we choose which one to pick up, right? We'll basically take the term 1 minus 4x, and if we expand this out, we'll see that 4 of x 4x will obviously be greater, so this would yield like a negative number, right? Because the positive outside, so this would always yield a negative number. We don't want that happening, first of all, because a, you cannot solve for negative square roots, and b, because it just doesn't make sense to have negative Catalan numbers. Negative Catalan numbers not exist. There's only positive Catalan numbers, right? So we need to have it as negative outside to cancel out the negative inside, and this would basically give us a sum of all. Basically, it would give us a generating function for all Catalan numbers, right? So this here is the generating function for the Catalan numbers, right?